Hello, my name is Matthias Troyer. I'm a technical fellow and corporate vice president at Microsoft, where I lead the teams working on quantum software and quantum system architecture. Today, I want to talk about the interplay between architecture and cost, because ultimately we want to build a cost-effective utility-scale quantum computer. Remember that utility scale was defined as being able to solve a problem where the value of the solution exceeds the cost of the computation. And thus, today I want to talk about also the cost of computations and how that impacts our architecture goals. The cost will determine which problems a user can solve. Our chemist user might ask the manager, what is the budget I have for the simulation? And then they have to stay within that budget. For that, we want to then also cut down the cost of what we want to actually compute. We talked about how quantum computers can let you solve quantum problems much more accurately than we can do classically. And that to reduce the cost, we ultimately want to then train AI models based on the quantum data so that one can then get to quantum accurate results just using inference from classical AI models. But first, I have to generate quantum data so that I can train the AI. And there, simulating the full molecule, the full material, can be costly. So the question is, can I do it more cheaply? And one technique that has often been used in quantum physics is to simplify the models. Simplify the model describing a material, a molecule, to a so-called effective model that is simpler than the full one, but still captures all the relevant physics. For example, when looking at the high-temperature superconductors like lanthanum, strontium, copper oxide, they consist of copper oxide planes. And the first step is to say, let's look at a single plane instead of the 3D stack of them. And then the next step is to simplify those planes even further by realizing that of all the electrons in there, the most important is the electron in one of the copper 3D orbitals. And we can thus simplify it further by replacing each unit cell of the plane by a single orbital and the electrons in those orbitals only. And that way one then ends up with a model that has one latticite per unit cell of the material. The next step is to further simplify it by reducing the long-range Coulomb interaction to just the strongest term, which is the on-site interactions between two electrons sitting on the same orbital, on the same atom. With that, we end up with the so-called Hubbard model, which is one of the simplest models in quantum matter physics, but is still exponentially hard to solve on classical computers. One can go even further by realizing that when the repulsion is very strong, then we will never want to have two electrons per site, but they will all spread out, which then in the half-filled case will be one electron sitting per latticite, and we only need to consider the spin degree of freedom of the electron and not its movement. And now this model becomes a quantum magnet. All the electrons are localized magnets that can point up or down or left or right. And the question is, what is the model describing this quantum magnet and what are its properties? So with that, we can start from simple models like a quantum magnet, go to a more complex model like the Hubbard model before we get to the full material in a crawl first, then walk, and then run approach. The next question then is, what do we want to simulate? The simplest and cheapest simulation is quantum dynamics. I take a quantum state and I propagate it in time. Because the electrons in the quantum magnets are basically like qubits. And it is no surprise that I can just use qubits to simulate how they evolve in time. Thus, the simplest applications may be the time evolution of a quantum state of a quantum magnet. We call that a quantum dynamic simulation. The chemist, though, might ask about energies. Because the chemist may be interested in chemical reaction, and for that, they need to know what is the energy barrier between the reactants and the product. So what is the energy I need to invest to overcome the barrier to kick off the reaction? And to get that accurately, again, we want to have a quantum computer. We talked about how we evolve a quantum state in time. And when you look at a molecular material in the quantum system, the energy levels will be quantized. That's where the word quantum physics comes from. The lowest state is the ground state, and then there's the hierarchy of excited states. And if I take one of these states, like the ground state, and evolve it in time, then the state picks up a phase. And the phase it picks up is proportional to the propagation time and the energy. And thus, in time, as I evolve that state, the phase of the wave function is the energy of the ground state times the time. Same for the excited states. The phase of those wave function will be just the energy of that state times the time. And the higher the state, the higher the energy, the faster the phase evolves. If I now propagate for a certain time and stop, and then measure the phase of the wave function, then measuring that phase tells me something about the energy. Because simply when I divide the phase by the time I propagated, I get the energy. And just like when I measure a qubit, I get a 0 or 1 state. Here, when I measure the phase, the wave function will collapse to one of the states. And if I started from a wave function that was close to the ground state, then most of the time when I measure the phase, I will get the phase corresponding to the ground state, with the energy of the ground state, and the wave function of my qubits will be the exact wave function of the ground state. That is the big advantage of quantum simulation, of a classical one, that I'll get this exact ground state and the exact energy. So, and all I have to do for that again is take a quantum state and propagate it for a certain time. It all comes back to something that is native to a quantum computer. So with that, we now see kind of what are the applications we can do in quantum simulation, quantum dynamics to the energy calculation. Next, the question is, what is the cost of that? For that, we again use quantum resource estimation that we introduced in lecture 3. First, to calculate the requirements at the logical level. For the chemistry problem in that lecture, we saw that for certain 56 orbital chemistry problem, I needed about 2,700 qubits and run them for about 1 billion logical cycles. The quantum dynamics problem on the quantum magnets might need just a bit more than 100 qubits, and I may need to run it only for a few million logical cycles. Thus, it is much cheaper, and hence those are the problems I think we'll solve first. For the cost, it's important, though, to also understand how often do I want to run it. The chemist may want to go through a reaction network and calculate accurate quantum energies for about a dozen configurations. For each one, they want to do it 3 times to make sure they found the ground state. The total, let's say, 36 configurations. And that's what we can use to estimate the cost. The next step then is to assume certain qubit types, qubit fidelities, qubit gate speeds, and calculate the physical requirements to match the logical ones. And then we want to know the number of qubits, the runtime, and what is new today, we also want to consider the cost of the computation. And that includes, on the one hand, the build cost. I need to pay for building the qubits, the control system, the reader system, the entire quantum computer. And I then need to consider the cost for amortizing the build cost over the lifetime of the machine. In addition to the build cost, I also need to include the operating cost. The cost for the building, for the security, for power, for cooling, operations, and maintenance. And to keep things simple, I assume a round number of $1,000 per hour. That corresponds to about $10 million a year, which seems the right ballpark for building and running a quantum computer. Now with that, our chemistry program that had about 1 billion cycles would take about 3 hours to run. With those 3 hours, if an hour costs $1,000, the total cost will be about $3,000. The user wants to run it 36 times, and the cost for doing that 36 times will be about $100,000. That seems reasonable on this fast computer with the logical clock speed of 100 kilohertz. But if the clock speed now is not 100 kilohertz, but only 10 kilohertz, then the runtime is not 3 hours, but more than a day. And the application cost will go up to $1 million. And if it's another 10 times slower at the kilohertz, then it takes almost 2 weeks to run it. And the total cost will be $10 million. So clock speed of the quantum computer will be very important for cost. The other ingredient that's important for cost is how many quantum computers do I need to build? Ideally, I build just one quantum computer. But we discussed that control and read at the scale is challenging, and we may want to actually build many networked modules. I could build it from 10 network modules or 100 modules. The more modules I build, the easier it is to build each of them, but then I need to use more and the cost will go up. If I combine those now, then I see a huge variation in the cost. If I can do the calculation with a single fast module, the cost may be as low as $100,000. But if I need 100 slow modules, the cost could go up to $1 billion. Coming back now to our chemist, she may hear that her budget is up to $1 million for the project. And with that, the chemist will want to actually now choose a quantum computer that is fast and consists of a few modules. So to reach utility scale and solve a problem where the cost is less than the value, we want to have, first of all, efficient algorithms and simplify the problem as much as we can to reduce the runtime and the qubit count. Next, we want to have fast qubits so that the runtime is short. Then we want to have systems with a compact footprint where I need few modules only, again, to keep the cost low. And that will influence our architecture. We will want to aim for high speed and putting as many qubits as possible into a module. Of course, there are trade-offs. It could be that building modules with fewer qubits is cheaper. It could be that building slower qubits is cheaper than building faster qubits, but those are the trade-offs that the system architect needs to consider when looking at the cost of the system. Thank you.